This is a review of the Lewis structure puzzle method that was presented in class. Just in case anyone's curious, this is the author. It was taken from the Journal of Chemistry Education from 1998, volume 75, issue 3. The steps in the puzzle method is basically ID the chemical formula. You need to know what atoms you're going to try and represent if you're going to try and put them down on paper. The next thing is you write out the Lewis dot structure for each individual atom. Use the neutral form, not ion. Again, use the neutral plain atom, not the ion. You would add additional dots that are free of any atom for any negative charges. You would also take away dots from any positive charges. We really won't be doing that much. If you're going to take away a dot though, my suggestion would probably be take it away from the least electronegative element. Next, you have to ID the central atom. In other words, what atom is going to be connecting, is going to have all the other things surrounded and bonded to it. The way to do this is pick the highest charge if the atom were an ion. That generally means something like carbon, which if it were to become an ion would become plus or minus 4. That's higher than oxygen, which if it were to become an ion would become a minus 2. Therefore carbon would be higher than oxygen. If the two atoms would have the same charge, then you go to the one that's lower on the periodic table. The example I'll use is oxygen and sulfur. Both would have a charge of minus 2, but sulfur is lower, and that's lower on the periodic table. That would be your central atom. We'll visit that one a lot with certain things like sulfite, sulfur dioxide. We won't necessarily do the sulfate ion, but we could try it anyways. Now that you have all your atoms and you decide what is the central atom, you fit it together like a puzzle. You try and match single dots to single dots. Each time you connect one of those single dot to single dots, you replace those dots with a line. That line is now the chemical bond, and it represents two shared electrons. Again, the line replaces the dots, and it represents two shared electrons in a chemical bond. The last step is probably the most complicated in this method, is that you rearrange your dots and your bonds till all the atoms but hydrogen have octets. All the atoms need 8 electrons either bonded or possessed around it. Hydrogen only needs to have 2 because it only has a 1s orbital, which can only hold 2 electrons. Last step is, if it is an ionic compound, make sure you do have brackets around the ion. We'll just be revisiting the examples that were done in class. This is basically just a review. It's not any additional instructions. It's just to serve as reference. So the first example we did in class was water. It has the deadly chemical formula of dihydrogen monoxide. Oxygen would have 6 dots. Each hydrogen would have 1 dot. Since oxygen has the highest charge at minus 2 as opposed to hydrogen, which would be plus 1, oxygen is the central atom. I begin by connecting single dots in both cases. That's what I'll end up with. I need to count my octets. Each hydrogen has 2 in the chemical bond for this hydrogen, 2 in the chemical bond for that hydrogen. The oxygen itself has 2, 4, 5, 6, 7, 8. Oxygen's octet is fulfilled. Hydrogen has its 2 electrons. The structure is sound. We have officially drawn water. Second example we did in class was carbon dioxide. Formula is CO2. Again, oxygen has 6 dots in its neutral Lewis dot structure. Carbon would have 4. To determine the central atom, we try and figure out the charge. Carbon would be a plus or a minus 4, oxygen being a minus 2, 4 being greater than 2, carbon will become my central atom. So I begin by connecting single dots to single dots. I'll do that for each oxygen on opposite sides of the carbon. I'll end up with these two bonded together. So I'll check the octets right away to see if I'm done with the structure. Oxygen has 2, 3, 4, 5, 6, 7. Carbon has 2, 4, 5, 6. Neither has octets fulfilled. Well, the good news is I still have single dots available, so I will join them together again. Now oxygen has 2, 4, 5, 6, 7, 8. Carbon has 2, 4, 6, 8. The oxygens are the same on both sides. Here's an example again of the symmetrical molecule that we talked about with polarity. Everything's octet is fulfilled. The structure for carbon dioxide is sound. The last example we did in class was the carbonate anion. The formula is CO3 2 minus. Again, 4 dots for carbon, 6 for oxygen, and here's what I mean by free-floating electrons. 2 extra dots representing the -2 charge. Again, the central atom in this case will be carbon. It has a +4 charge if it were to become an ion. Oxygen would have -2. The electrons each have a charge of -1. So carbon being 4 is bigger than 2, and it's also bigger than 1. Carbon becomes your central atom. Note when I'm drawing this that I do keep the electrons free floating up here so I don't lose track of them. I begin by making my single joints. So I'll join these oxygens, these carbon and oxygens, and that will give me this. Each oxygen, in case you haven't noticed, is bonded by 2, 3, 4, 5, 6, 7. Its octet is not fulfilled. Carbon has 2, 4, 6, 7 electrons as well. Its octet is not fulfilled. Well, I don't want to lose track of my electrons, so I'm going to assign them right now. A good rule of thumb, but it is not part of the method, but it does make sense by what we know about periodic trends, the most electronegative atom would probably attract the electron that is free floating. So I will assign an electron to an oxygen which is more electronegative than carbon. In the actual method, it does say put the electrons on the outer atoms first, most electronegative second. I tend to like electronegativity more than location. But once I do that, if I check my octets, I see that this carbon still has 7, this oxygen has 7, but these 2 oxygens now have 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. The bottom 2 oxygens octets are fulfilled. Now, does it make a difference when I'm assigning that lone electron which oxygen it goes to? No, they're all equal, they're all the same. As long as they're in the outside, one oxygen is as good as any other. So I have one last free bond, free space where I could pair up, and that's what I'll do. These oxygens are already safe. Let's check carbon 2, 4, 6, 8. Carbon is now satisfied its octet. This oxygen now is 2, 4, 5, 6, 7, 8. That oxygen's octet is fulfilled. Remember, this is an anion, so the structure is not complete. The structure is considered complete once we put